let's wait 1 minute and then we can start.
Hello, Arena.
Okay, let's wait. Let's give people 30 more seconds and then we start. Okay, now the number seems to stabilize. Okay. Okay, good afternoon, everyone. My name is Francesco Petruccione, and I'm the interim director of the National Institute for Theoretical Physics. And I have the pleasure to invite you to our NITheP Colloquium. Yeah? Today's speaker is Prof.Kanshukan Rajaratnam from the University of Stellenbosch. Professor Rajaratnam is the director of the School for Data Science and Computational Thinking at the University of Stellenbosch, which is a fairly new addition to the University of Stellenbosch. His background is in chemical engineering first, then industrial engineering, and he wrote his PhD in systems engineering. Yeah? And if that was not change enough, he joined at some stage University of Cape Town in the Department of Finance and Tax. Yeah? And somehow that topic seems to be a constant now in his academic activities. Yeah? He's a member of the South African Young Academy of Sciences, which speaks for his young age, I guess. Yeah? And he has served also on the executive committee of the same Academy of Sciences. Professor Rajaratnam, we are very happy to have you with us today. On the panel, you will see also Amira Abbas. Amira is a PhD student in my group at the University of KwaZulu-Natal. And although she's working on quantum machine learning, she has a more financial background in a previous stage of her career. And she kindly offered to assist us with the moderation of the questions after the talk. And for those of you that are new to this Zoom game, at the bottom of your screen, you will see a bar with a question and answer button. And during the talk, you're most welcome to pose your questions there. Yeah. And Dr. Sinaisky, who you also see on the panel, he's co-hosting the event and is a kind of backup plan in case something happens to my internet connection. Yeah. So Professor Rajaratnam, people are here to listen to your talk and not to me talking here nonsense. Yeah. So please, over to you.
Cool. Over to Thank you, Professor Petruccione. So what we're going to talk about today is on some sort of consumer credit models. And this work was done a couple of years ago, but it was never completed and I'll talk about why it was never completed, because it's almost impossible for an academic to complete it. We need to actually partner with the bank to complete it, because it would depend on us giving out loans to people. And as academics, we don't have banking license. But essentially what I want to talk about is the rationale for that work. So in consumer lending, or in banking in general, a big part of research is forecasting default probabilities for consumer loans. And these are usually at acquisition stage. When I say acquisition stage, I mean when you first initiate these loans. There are two primary ways to improve these forecasts of probability of default. One is, you could use better statistical methods, and over time we've seen, really good methods coming out, or you could use more predictive input variables. And typically, the type of input variables are application data, which you find on an application form, demographic information about the applicant, and then you can get past financial history about an applicant, for example, from a credit bureau. Some things like, how many accounts have they held, how many have they been, they haven't paid back on, how many loans they haven't paid back, etc. Overstreet and his friends did some work in the early 90s, which said that flat maximum effects suggest that there is little performance difference between the various types of statistical models that can be used to assess applicants, given roughly the same data as input. In other words, you are not going to get improvement in forecasting, by improving statistical methods, or you're not going to get large improvements in forecasting. You'll get some improvements, but what you really need is new data that would differentiate, that has information value to the data that's already being used. In other words, new characteristics or variables. So what we want to do in this paper is we want to use, consider use of alternate data. Can we figure out some other forms of data that might be able to help us classify consumers in their risk profile? In order for me to talk about this, I must really talk about a little bit about, consumer loans economics, right? Essentially, what we want to do is, if we give somebody a credit, can we work out their expected profit? In other words, will they be profitable to us? And in a simplified model, if you imagine there are two outcomes of a person for a loan, for a borrower, either good or bad. If they are bad, they default sometime in the future, within a window period. If they're good, they do not default in that time. And of course, these are mutually exclusive outcomes. If they don't default, we get, the results in a revenue of G. And if they do default, then we lose L. And therefore, we can work out the expected profit of an individual or for a borrower. And of course, PG plus PB equals 1 because they are mutually exclusive, and they are the only two outcomes. And therefore, PG equals 1 minus PB. In other words, we can characterize expected profit based on probability of default of an individual. So we need to work out a method to forecast this probability of default for every applicant. So then we can decide whether to give them credit or not based on their expected profit. Before, advent of IT, credit applications were manually evaluated. Applicants would, they would use their existing debt to figure out if they should be, we should give them more debt or not. There will be a relationship with the bank, and the bank manager might look at their cash flow statements. In other words, are they saving? Do they have a lot of expendable income, etc. As application numbers grew, of course, this wasn't feasible, and the cost was heavy. So, with improvements in IT and statistical scorecard, it allowed for quicker evaluations of applications, and you could evaluate in greater numbers. I guess they went to, hand in hand. As the methods improved, more people started applying because you could actually process their application. And banks had a wealth of historical information on previous applications. They have access to data, and they could use this to build models. When you're talking about consumer loans, you're talking about, a bank could easily have million historical loans to build data, to build models on. So this allowed for ease of building models. And these output of these scorecards were credit scores, or they're called credit scores. And these credit scores really is an assessment of the likelihood of an applicant to default. It measures the defaulters relative to that applicant's population. So if you look at this diagram there, if you imagine there were historical accounts for Jack, Jill, Mary, Snow White, and the 7 dwarfs, and you built some score around them, and you knew whether they defaulted historically or not, you could essentially put them in some sort of bands, and within that population that falls in that band, you'd know what proportion of them defaulted. And then if Kanshu and a different Mary came around and you had to score them on the scorecard, and let's say Kanshu had a score of 755, then you could look in the bucket to figure out what the estimate of probability of default is. This assumes that these are all discretized into buckets, but in reality, they're continuous variables. So inputs into these scorecards to get the score typically were information that was available at application stage. So what information is available at application stage? So if I apply for a loan, there's an application form I fill, and on that there will be various things that I have to fill in, or various things about me. And those are all information that could be used in a scoring model. And that information could be things like whether I rent or own where I live, my postal code, etc. There might be information about the demography of the person. So, for example, maybe based on where they live, there's some characteristics about that person that you might know. And then you might also use, using their ID, you might check their information on the credit bureau to see how have they fared with historical accounts, that weren't held by this particular bank, and have they done well or not. And therefore, you could use, these are all information that's available at the application stage. So when you build a model, you can use all these as input variables. And some of them will have information value and others will not. Because the outcome is default or no default, and is binary, it lends itself to logistic regression models. But there are various models that banks have used since logistic regression. But logistic regression still remains very popular in building these models. Then, as I said earlier, then Kanshu comes along based on his information that's available at the application stage. You could score Kanshu and then determine what their probability of default is. Essentially, the score is mapped, has a one-to-one mapping to the probability of default. So what does this all mean in terms of an applicant, in terms of their profitability? So we know there's a one-to-one mapping between probability of between score and probability of default. We also know from that equation there's one-to-one mapping between probability of default and expected profit of a person or of a borrower. Therefore, there's a one-to-one mapping between score and expected profit, and that's what you see on the blue graph. There's a one-to-one mapping, and generally you build the score such that the highest score has the lowest probability of default. Therefore, the highest score will have the highest expected profit. So, because this is well ordered between score and expected profit, if you wanted to give somebody, one person a loan, you'd obviously give to the person with the highest score, because that would result in the highest expected profit. And that you see from the blue graph here. Right? And because of the well-ordered nature of the score, it also lends itself to a single cutoff score policy, which means if I decide on a cutoff score, let's say I decide on a cutoff score SC, it just means I will accept anyone who has a score above SC and reject anyone with a score below SC. Accept means I will give them a loan, and reject means I will not give them a loan. A portfolio manager with an objective of maximizing expected profit will give anyone a loan whose expected profit is greater than 0. So it would be, I don't know if you can see my cursor on Zoom. It was where my cursor is at the moment, where the blue line crosses the horizontal line. Because anything above that, the applicant would have expected profit greater than 0. Okay. The next few slides are not really important to my talk, maybe the next 4 slides, but let me just go through them anyway, because I think it helps to understand how one thinks about these consumer loan models. So I talked about a portfolio manager. I'm just going back a slide. I talked about a portfolio manager, maximizing expected profit. And if they maximize expected profit, you would give anyone a loan whose expected profit is greater than 0, right? Because they would result in positive revenues for you. But a portfolio manager doesn't only maximize profit. They live in a world of multiple but conflicting objectives. So they could maximize profit, they could maximize market share, or they could minimize expected portfolio loss, right? In our work in general, since Oliver and Wells's work in 2005, people have generally looked at expected profit and expected volume to show for these kinds of examples. So we'll restrict ourselves to 2 objectives. The controls available to a portfolio manager is a yes or no decision on each application. And the portfolio manager has access to credit score on each application, right? So you have a pool of applicants. You can score everybody on using your scorecard. You have a credit score on each one of them, and you have to decide yes or no for each applicant now, right? On the left-hand side is the blue graph from the previous, about 2 slides ago, which is the mapping from score to expected profit of an individual. On the right-hand side is the mapping of a cutoff score to portfolio profit. So on the left-hand side is the expected profit of an individual, and on the right-hand side is the expected profit of a portfolio. So what do I mean by that? Right? So if I had to give one person a loan, I'd give it to the person who scores at point D, right? Because that would give me the highest expected profit. And because we are talking about continuous variable here, you know, at D will have 0 people and 0 profit, right? I'm just going to the next slide. But if we wanted to increase the number of market share, what I would do is I would give the next highest person a loan, right? And now our portfolio starts increasing in size and in expected profit. And if we keep on decreasing our cutoff score, so let's say our cutoff score is C, which means I will give everybody loans whose score is greater than the cutoff score SC and reject everyone below SC. And my portfolio profit would be on this point. I don't know if you see my cursor. Amina, can you tell me if you can see my cursor?
Yes, we can.
Oh, okay, great. So in that case, then my portfolio profit would be where my cutoff score would be. And of course, if I reduce the cutoff score and I come all the way down to point B, anyone above that would give me positive expected profit, and any borrower with the score less than the cutoff score at B will result in a negative profit. So I wouldn't give them a loan, right? Because my cutoff score is at B. And that would be my maximum portfolio profit point. And if I keep on decreasing the score, then because I'm accepting people who result in negative expected profit, my portfolio profit also starts decreasing, right? Until it decreases to when you accepted everyone. The black line over here, or I call it BE, we call that the efficient frontier because it's the point of, it's not dominated by any other operating points. It's the point where you can get, it's expected, maximum expected volume and maximum expected profit, a portfolio profit, and they don't, each point do not dominate another point on that curve, right? So if you're a bank manager, you would probably cut off somewhere between B and E if your objective was only to maximize profit and maximize market share, right? Okay. So you could see how credit score is really integral in making these decisions about giving somebody credit or not, because that determines whether they are profitable or not, right? So credit scores essentially map to expected profit and hence important for decisions on application. What credit scores do is they reduce the information asymmetry between a bank and a loan applicant. So if you imagine a model with no variables or no characteristic variables, or in machine learning, no features, right? Then you wouldn't be able to differentiate between applicants. And each applicant would have equal likelihood of default, right? But as we add variables to a scorecard, we start differentiating applicants. So if you think about income as a differentiator in risk, in fact, it's not, but let's just assume it is. And let's assume higher the income, the lower the risk. Then if I know somebody's income information and that becomes an input into a scorecard, then we can differentiate risk probability of default between two applicants, right? And banks use all sorts of variables from multiple sources to reduce this information asymmetry. So I talked about earlier about application data, credit bureau data, and demographic data. When I worked for a bank a long time ago, we used information such as zip codes, right? And then we'll figure out in a zip code, in that particular zip code, how many gas stations were in that particular zip code. And that happened to add value or information value in predicting default probabilities. And of course, this needs to make sense, right? And nobody really made sense of it at that time. I suspect the reason why it makes sense is maybe if there is greater number of gas station. It could do with the number of population, but given population, taking population number out, it could also have to do with affluence and access to, vehicle, etc. Right? And somehow this helped to predict default risk. But as the flat maximum tells us that, we need newer variables. We don't need newer ways of evaluating these variables in order to build credit risk models, right? And so can we reduce information asymmetry using new variables? Or where can we find these new variables? That's really the question that I want to answer in this talk. So in past work in consumer lending, sorry, my slides are very verbose, so please don't read. I mean, I think you can just listen to me. I have some pictures later. So in consumer lending, general research looks at making a single offer by a single lender or bank to a single consumer, right? But that's not how life works, right? Because as a consumer, I get multiple offers. Those of you who have lived in the UK and the US and in Canada, you would have received offers all the time from banks such as Capital One and Citibank through mail, right? So direct mail. And of course, multiple banks are making multiple offers, and they are making to multiple people, and there are multiple decisions a single consumer can make. Right? In this research, we consider a lab experiment where a single consumer receives a sequence of offers, and they have to make this decision on the sequence of offers. And maybe from the way they make these decisions, we can, find a new variable that will differentiate this or add information value to a scorecard model based on this new variable, right? So past literature have talked about consumers receiving a sequence of finite offers. In fact, I only know of one paper that talked about it, and that was a paper written by the same authors as my co-authors here. And the idea is you have n offers, and these offers vary based on some characteristics. Let's say interest rate or APR, right? And of course, you can rank them better to worse. So if you're borrowing money, or if think of this as a credit card, you'd obviously want a lower interest rate than a higher interest rate, right? So ordering is possible, but the order of offers are equally likely. So I could receive, let's say, a 17% interest rate as likely as a 10% interest rate, right? And the order of receiving this interest rate within a band is equally likely, right? But the point is that as a consumer, I can order them. I can figure out which offer is better than another offer. When faced with this loan offer, a consumer has to make a decision, right? So they can either decide to accept an offer or reject an offer. Now, if you've worked in if you received a direct mail offer before, they always have an expiry date, usually 2 weeks. So within the 2 weeks, you have to accept this offer or reject the offer. So we simplify our scenario such that you either have to make a decision. If you decide yes, you get the card, or you can apply for the card. If you decide a model here. The consumer obviously has the objective of maximizing the probability of taking the best offer. They want the lowest interest rate as possible, right? This scenario can be modeled precisely in terms of an optimal stopping problem known as secretary problem, which is a secretary problem is well studied in operations research and probably in computer science. So what is a secretary problem? So secretary problem is a sequential decision problem where a hiring manager has to interview n applicants, and they know what the value of n. And there are n people applying for one secretarial position, right? So manager interviews the first person and has to make a decision whether to hire the person or not. If they hire the first person, then they don't interview the other n-1 applicants, right? But if they decide not to hire the first person, then they interview the next applicant, the second applicant. and they can never go back to the first applicant, right? And then they interview the second applicant, and if they decide yes, then they don't interview the N-2 applicants who would have come after them. But if they decide no, they interview the third applicant. So of course, what you're doing is you're looking at the applicant and you're trying to figure out whether you will get a better applicant in a later round than the applicant you are seeing now, right? If you go all the way to the nth applicant, you have to take that person because that is the last applicant, right? So when you are looking at the N-1 applicant, you have to decide whether that applicant will be better than the nth applicant or not. And you could make this decision based on past experience of interviewing N-1 applicants, right? And you know the kind of population that you're seeing. The important point is that the person who's interviewing can rank order the people that they've seen earlier and the person they're currently seeing. In other words, they can see who's better and who's worse, right? Past research considered whether the result of the subtlety problem could be used to time a direct mail offer in consumer lending. Here we want to see if we can use this to figure out a new variable that can be used in credit models. So let's look at a practical example of a borrower's decision policy, right? So remember, they want to maximize the probability of accepting the best offer. In other words, they want the lowest interest rate. So let's say they receive the following sequence of offers. It's kind of where my cursor is, right? 15, 12, 17, 18, 16, 19, 11, 13, 10, and 20. And I want to define something called a candidate offer. Candidate offer is the best offer they've seen up to that point, right? So when they receive the offer of 15%, that is the best rate that they've seen up to that point, right? So 15 is a candidate offer. Then when they see the second offer of 12%, that's better than all the offers they've seen before, which is 15%. So 12% is a candidate offer. Then if they see 17%, 17% is not better than the best offer they've seen up to this point. Therefore, 17 is not a candidate offer. Neither is 18, neither is 16, neither is 19. And when they receive 11, 11 is a candidate offer because it's better than everything they've seen historically. 13 is not a candidate offer, 10 is a candidate offer, and 20 is not a candidate offer. So we needed to define a candidate offer because the optimal policy for this person who's trying to get the best offer is to reject approximately the first N over E offers and then accept the next candidate offer, right? So if N was 40, they would reject about N over E, which is about 13 offers, I think, or 14 offers. They would just reject the first 14. They will observe what the numbers are like. Then they will look at the 15th offer. If 15th offer is better than all the offers that they've seen before, then they will take that loan. If it's not, then they will look at the 16th offer. And then if 16 is the candidate offer, in other words, is better than the first 15 offers, then they will take it. So they will accept the first candidate offer after the first N over E offers. If they do this, then the success of the probability of success is about 37%. Right? So that's the decision policy that they should use to maximize their probability of success. But of course, not all applicants or not all games, you know how many people you are interviewing or how many offers you are going to get. In other words, you don't know N. There's also a decision policy for that. And the decision policy, if you use that decision policy, it would also result in probability of success. In other words, probability of getting the best offer at 37% or 0.37. Searle and Rappaport and Shank and Winter did this human decisioning and looked at how people make decisions. right? When they faced with the sequence of offers in the scenario I told you, which is they have a sequence of offer, and at each offer they must take up the offer or reject the offer. If they reject the offer, they can't go back to it, and they also know how many offers they're going to get. In other words, they know n. And Searle and Rappaport found that there's generally 3 types of decision rules or decision heuristics, right? The first rule is the cutoff rule that people employ. The cutoff rule is they decide on a value h, and they observe h1 minus applicants. And then they accept the next candidate offer, right? So in other words, if h was 15, they would observe the first 14 candidates. They will not accept any of the first 14 applicants, right? Then they will go to the 15th applicant, and they will take up the 15th applicant if the 15th applicant was better than the first 14 applicants. In other words, if they were a candidate applicant. If they were not, they would reject them. Then they would look at the 16th. They would keep on doing that until they get to a candidate applicant, and then they would accept the candidate applicant. And we call that the cutoff rule with parameter h. There's also the, yeah?
Are you open to taking questions now, or shall we?
Sure.
Okay, so Herman's asked, why did we not take 13%, or why did we not start from 12%? Because 12 was less than 15%.
So why did we not start at, sorry, over here?
Yes.
So it's a candidate offer is not the best offer. Candidate offer is defined as the best offer thus far. So after 15, the best offer is 15, right? After the first round. So maybe the person can tell me if they understand what I'm saying or not. I can't see the chat room.
Okay. Yeah.
So after the first round, when they get the 15%, that is the best offer at that point. So that's the candidate offer. After they get the second offer, or if the second offer comes around, then 12% is the best offer. So that's the candidate offer. So candidate offer is not the best offer. If you look at the totality of offers, it's the best offer thus far.
Perfect. Thanks.
Okay, cool. So there's a difference between the best offer and a candidate offer, right? So the person's objective is to get the best offer, but we have to define candidate offer in order for us to define, to talk about different policies that people employ. A second policy, a decision rule, some people employ something called successive non-candidate voting rule. So they look at a whole lot of people, they decide on a parameter K, and then they look at when they see first candidate who follows K successive non-candidate applicants since the last candidate. So if I go to the previous page, say they see 12% and their K value is 3. So then they will go 17%, well, that's not a candidate offer. 18%, that's not a candidate offer. 16%, that's not a candidate offer. So they'll, since their K value is 3, they will look for the next candidate offer. So the next candidate offer is 11, and they will accept 11% as the best, as the offer that they take out, right? Because they don't know what's coming after that. So these are decision rules that people employ. The third decision rules that people may employ is which they select the next candidate once they've seen L candidate offers. So they wait for L candidate offers. They decide on a parameter L. They decide on an L candidate offers, and then they'll take the next candidate after the L candidate offers, right? And Searle and Rappaport saw that most people make decisions based, or their decision-making heuristics can be defined as one of these rules. But the best way to make a decision is to use a cutoff rule policy with h minus 1 approximately equal to n over e, right? But people don't know that, so they don't necessarily use that rule, right? And if you could work out each person's decision-making rule, or how they make these decisions and their parameter, that's the characteristics about a person, right? And that characteristic about a person might tell me something. So let's say Kanshu is, it makes decisions in these kind of scenarios using a candidate counting rule with parameter L equals 2. That might tell me something about the risk riskiness of Kanshu, right? So in other words, can we figure out decision heuristics of a person, and maybe that would tell me something about that person. We don't know if it does, but maybe it will tell us something, right? Of course, while I talked to you about optimal decision-making rule, I've also told you 3 different rules, and each one of them are having different parameters. In other words, there's a lots of ways people are not making optimal decisions, right? And they're making non-optimal decisions because they could be risk-averse or risk-seeking. The experiment we assume we do assumes risk neutrality. It could also be that because they have limited cognitive process capacity and they have a satisfying behavior. In other words, they see something and they want it, right? And some individuals may just be hungry for credit, so unwilling to let an offer pass by, right? So, for example, if you are hiring a secretary and you're desperate for a secretary, you might just hire somebody who you don't think is necessarily the best you're going to see, but because you want the person now. So there's lots of reasons why people don't behave optimally, right? But we know that in this kind of scenarios, generally people behave with 3 kinds of decision rules with various parameters, right? And taking this away from secretary problem to direct mail offers, we've seen where this works in the direct mail offer, right? So please don't read through this. I'll just tell you what happened, right? So when I was working in a bank, we'll offer to a group of people, we'll send them a direct mail offer, right? With a certain interest rate. And some of them, about 1% of them will take up the offer. 99% of them will say no. A month later, we might offer, let's call the first set of people portfolio A, right? The people who took up the offer in the first round. Then a month later, we might offer the group of people who did not say yes, a second offer. It might be exactly equal to the first offer. In other words, the same interest rate, or a portion of the people might get a better offer. And you find that now, even though they said no earlier, some of them, even despite the fact you give them the same offer, now take up the offer in the second round. And repeatedly, we saw the people who take up the loan in the second round, on average, had a lower risk than the people who took up the offer in the first round, right? Even though they were the same people we made offers to in the first round. In other words, it seems to indicate that the decision heuristic rules might matter for credit risk, right? And that our credit risk models were not picking up these decision heuristics through other means or through other variables. In other words, they were not correlated to the other variables that we are using. It seems to indicate that, but we didn't prove it, right? And we don't prove it in our research here too, because we are not a bank. So we want to estimate decision heuristics. And so we can run an experiment in a lab setting to figure out individuals' decision heuristics, right? I'm just going to gloss over the slide because I think we are running out of time as well. But in Searle and Rappaport, when they did it, a person could look at the quality of an applicant. In other words, they can look at a CV of a secretarial applicant and say whether they were better than the previous one. In other words, they can rank them, but they couldn't really talk about the quality as such, right? In our case, we give them a rank and a quality, and we tell them where they rank compared to previous ones that they've seen, right? And an alternative, so that's a secretary problem. A full information secretary problem is where the person has access to the distribution of quality of applicants. So they know something about the distribution of the applicants that they're going to see. And there's an optimal rule for that. It's called a biased optimal rule. And if a decision maker follows the biased optimal rule, they would end up choosing the best applicant 58.7% of the time. Right? In other words, if you knew the distribution of the kind of applicants or loans you're going to get, you could make better decisions, right? And you could get you could end up choosing a better decision about 60% of the time. And so we simulated this, where we inserted the best decision in the first round, in the second round, etc. And here I compare the cutoff rule to the success of non-candidate policy and the bias threshold policy. And in every case, the bias threshold or policy ended up performing better. And so that policy, if somebody follows that policy, they would always do better than somebody who follows a cutoff policy or a success of non-candidate policy. Anyway, we wanted to set this up in a lab setting. So the lab experiment was the following. Each person was given 40 offers, and they had to decide whether they wanted to accept an offer or not. And of course, they were given consumer loan offers, in other words, interest rate. That's all they got to see, an interest rate, and they have to decide whether they wanted to accept that offer or not, right? With this, we also had to give them some sort of cash rewards, because economists have seen that if you don't give them cash reward, people don't always behave in an optimal manner in line with what you're trying to study. So what we did was, for each win, subjects were rewarded 20 rands. They played 100 games, so they had the potential to win 2,000 rands. And if they won more than 50 rounds, they would win another 500 rands. So the maximum possible reward was 2,500 rands. And this compared well with, let's say, social grant applicants at that time who received 1,500 rands. And we didn't discount this, right? Because that induced this credit hungry behavior where you try to win more in earlier rounds than latter rounds. Subjects were, we recruited them, the Faculty of Commerce at UCT. We initially did 28 subjects. We studied 28 subjects, and we analyzed 26 of them because 2 of them, the data was not usable, right? And so this is what the game looks like, right? It was a simple game that was devised. So if you're an applicant, oh, sorry, you can't see it at the moment. So let me share that slide. So can you see a black screen?
Yes.
Okay. So you're going to play with this with me, Amira, right? So essentially, you're going to see, I mean, these are all the rules. For time's sake, let me not go through the rules. You know there are 100 or 40 rounds coming, right? 40 offers. The first offer you see, which is offer number 1, is 16.9%. And of course, this is the best offer you've got so far. You have to decide whether you want to take this or not. If you take this, you don't see the other 39 offers, and this is the offer that you take. And your objective is to get to the best interest rate. So do you want to say yes or no?
No.
No, okay. So the next round is 19.5, which is the second best offer you're seeing. So would you say yes or no?
No.
Okay, so you can just tell me no or yes.
No.
So, no, okay.
No. Maybe.
So
this is the first candidate offer, right? So
the second candidate offer, because the first offer is always a candidate.
Right. Offer. Okay. I'm gonna say no.
No. Okay.
No.
Okay.
So
you can see it's a candidate offer by looking at the rank of this offer, right? Because it ranks based on the previous applicant.
Perfect. And there are 40 offers in total.
Yeah.
Oh gosh. I'm going to say yes.
So it turns out yours was the 9th best you would have gotten in your series of 40.
Okay, that's not too bad.
Right? But your objective was to get to number 1, right?
Yeah.
And you would have had to wait until the 20th offer, and you have got 13.7. So 13.17 as opposed to, what was it, 15.47, right? So essentially that's the game that the people are playing. And if they got to the 20th offer, they would get 20 rands, and they played this game 100 times. Now, how do I stop this? It should come on top, right? Now I can't seem to get out of this. Yeah. I wonder if I close.
Stop sharing your screen. Okay.
Yeah.
No, it didn't give me that offer, but if I close it, it came right. It didn't give me the option to stop sharing for some reason, but it's fine. You see my PowerPoint now, right?
Yes.
Okay,
Yes.
thank you. So those 26 applicants played 100 rounds. There were 2,600 rounds, and it turns out that people chose the best offer 821 times. 107 times people chose non-candidate solutions before they got to the 40th offer. In other words, they just saw it and they took it, even though it wasn't, they could have waited until the 40th offer. This could be because of boredom, right? Searle and Rappaport says it could be because of boredom, or because they're playing so fast that they press yes by mistake. And in 423 rounds, people waited until the 40th offer because they thought they would always get better offers. And this indicates patience. So these are characteristics of an individual that we may be able to use in our studies to figure out whether they're risky or not. Okay, why is this not going? Okay, right. So the output of each subject, looking at the 100 outputs, we could class them as, being any one of those decision policies that we talked about. Candidate cutoff with a certain parameters, candidate candidate count, successive non-candidate, or bias threshold, right? So we can infer their decision rules from each one of these. And we could label them as such. So if you could label each person with their decision rule, that's information about someone that I could potentially use in my scoring models, right? And this, using my example of what I saw at the bank, we could not infer using our credit card models because, when we offered them the same offer in a second round, some people seem to take up that offer, right? In other words, they wait for better offers, or in the meantime, they've got offers from other banks, and they've realized, okay, this is the best offer they're going to get, and they end up taking up the offer in the second round. Right? We did some study. We compared the bias threshold people who use the bias threshold decision rule to compare to other people, and they won more rounds than anybody else, and this was statistically significant. And those who employed the bias threshold rule seem to have waited longer than those who employed other decision rules. In other words, they seem to indicate patience, right? Okay. So if we let people do such experiments, we might learn something about them, right? So each agent's decision can be attributed to a decision heuristic, and each applicant has a decision heuristic. So what can we do? We can ask each bank loan applicant to play this game, and then we can estimate the applicant's decision heuristic. And now we have a new variable about that person. We could potentially use this new variable to in a scoring model to work out whether this gives us information value about their risk, right? But there is one catch here, right? I used the fact that I knew that the 3 types of decision rules based on Searle Rappaport's work to classify people, right? I just replicated his work in this lab experiment. But you might have another game where you might not be able to classify agents based on their decision rule, right? And this is where machine learning comes into, or artificial intelligence comes into play. You could use something called inverse reinforcement learning to work out reward function of what agents are trying to optimize. So in other words, you look at the measurement of an agent's behavior over time. You might look at their sensory input, and if available, a model of the environment, and you want to try to determine a reward function that an agent is trying to optimize. We could use inverse reinforcement learning, slightly changed, to label candidates, right? And Chow and Beeling worked, they devised something called the behavior-based agent recognition. So here you recognize agents based on their sequential behavior. So you observe people playing their game. And then you decide whether you could classify them into different kinds of decision makers without having any preconceived notion of decision rules, right? The way I did it, I used Searle and Rappaport, but if you use inverse reinforcement learning, you don't have to use, or you use behavior-based agent recognition, you don't have to have preconceived notion of decision rules. For example, if you observe people driving or sequential behavior of people driving, you might be able to classify drivers as aggressive or defensive driver. And based on aggressive or defensive driver, you might have different, you might have different policy towards them. For example, this might be important for insurance companies or for medical aid, etc. Right? Similarly, you can also work out if two agents have similar behavior pattern or not, right? In our problem, we could use BAR or based on behavior-based agent recognition to work out decision heuristics of applicants if you let them play some sort of game, right? Okay. Chow and Beeling, used IRL and much more simpler methods such as PCA to recognize agents. And they wanted to see if our BAR/IRL will perform better than an unsupervised learning method such as principal component analysis or PCA. And here is their results based on simulating 300 three decision heuristics of a secretary problem of 300 agents, and they inputted that into a principal component analysis study versus an IRL study, and they mapped this onto a two-dimensional space. On the left is the results from the principal component analysis. You could see cluster one, those agents using decision behavior one are well clustered together. But there's some confusion between decision rule 2 and 3. It's hard to estimate. If you didn't know who was 2 and who was 3, it would be hard to estimate, differentiate between 2 and 3 in that portion of uncertainty on the left-hand graph. If they used behavior-based recognition, agent recognition, they classify pretty well, right? They classified decision rule 1, 2, and 3 well. There was lower variance in the same group, and there was, and there was increased distance between each group. So in other words, this method could be used to classify agents, right? So I think my time is up. My final remarks. So the purpose of the study was the following, right? Flat maximum told us that it's better to find new variables than necessarily new methods. You'll get more kick out of getting new variables. But we know banks use all sorts of variables, right? So it's hard to find new variables. What we want to do is reduce the information asymmetry between an applicant and the bank, and maybe the way an applicant thinks could be an indication on their risk profile. In other words, if we can figure out their decision heuristic on some game, that could have information value on their risk profile, for their risk profile. We know based on past practical experience on working in a bank that decision heuristics in a sequential offer behavior or environment seem to indicate that decision heuristics matter, right? And so we played a game with participants, and we worked out what the decision heuristics is. But we also showed that by using BAR, we don't have to have a preconceived notion of agent decision rules. We could cluster them into different behavior based on their decision rules, right? However, we couldn't do this experiment in practicality to see if there is a mapping onto their credit profile, risk profile. The reason for that is for us to do that, we have to give somebody credit. And as a university faculty member, I am not allowed to give somebody credit, right? Only a bank with a banking license or an institution with a banking license can give credit. So the next step would be really to collaborate with the bank and to test the viability of these decision heuristics to be used in scorecard models, right? That's all I have for you folks. Let me know if you have questions. Before I get to questions, Amira, I just have one thing, right? So I know there's a lot of physicists here. And when I presented my first paper to Bob Oliver is this brilliant OR guy, he's an emeritus professor from Berkeley. He listened to me and he said to me, Kanshu, I understand the math of it all, but can you explain the physics of it? I had no idea what that means, so I hope I don't get a question like that. Thank you.
Kanshu, thank you very much for the very interesting talk. And you know, I think your talk was perfect for our colloquium, because one of the things that we want to convince people of is that how important is mathematical science, theoretical physics, computational science for our everyday life. Yeah. And what you have shown us is that you know, even the human decision making should better follow an algorithm than just than just an arbitrary gut feeling. Yeah. So that and it also reminded me of a book that came out, I think probably 5-6 years ago, whose title was "Algorithms to Live By." Yeah.
Okay.
It was also a collection of algorithms that one should embrace in everyday life to win the various games that we play every day. Yeah. No, Kanshu, thank you very much for the nice talk. Amira, are there questions for Kanshu?
Yes, there is one from Arena. So she says, to what extent can consumers gain the outcome of an application by understanding the underlying algorithm without that reflecting their real risk profile? Good question.
So, good question, Arena. So one can, right? So people are already gaming these kind of models by, for example, depositing money into their savings account. So it reflects on the credit bureau, or in the bank, actually, not in the credit bureau. And then they look as if they have lots of money in their bank account, right? So with the game, it would be much easier. But then if this works, what we can do is start figuring out whether we could have multiple games and keep on changing games as we go along, right? And testing multiple games as we go along, right? Because there's an infinite amount of games one could play.
If in the meantime someone wants to type a question, they can. But can I ask? So what about if somebody has like a hybrid decision process, right? So under certain circumstances they behave in one way, and then after a certain amount of time they change their behavior.
So a good question. So what one needs to do is, you know, look at the time behavior of these decision making, right? So the time behavior could be almost in a short period or a long period, right? So one of the things that I've been thinking about lately is over long period. As people get more experience in life, not in the game, just in life, do they change their decision rules, right? And I think they would, right? If you're a child, you would probably choose very randomly, right? But now you can think about sequences of where you don't choose so randomly. You start thinking about candidate offers, etc., right? Now, do people change decision rules even within one sitting of a game, within 5 minutes? And you see that, right? So here we label people based on, you know, if on the decision rule they used mostly, right? But you could probably then build a model which says, what is the combination of decision rules that people are using, right? And work it out from that point. This is a very simple game that we are playing here. But yeah, people do change rules, I believe, but especially over a long time.
Okay, and then I think just one last question from me, and I will stop since there are no more. In the reinforcement learning regime, you have to maximize against some reward, and then you need typically some kind of cost function or some way to measure this reward, right? So if you don't know what the future offers are going forward, then how do you set this cost function? Like, what do you maximize against?
So you're playing this game with yourself. It's an optimal stopping problem, right? Where you are deciding whether future offers would be better than the current offer. So there's a cost to waiting and cost to not taking it up. So there's a trade-off that you're playing all the time.
Okay, perfect.
Cool.
Yeah. Can I, Kanshu, ask you a crazy question that is not really related to what you said, but it just came up to my mind. You know, there are situations where maybe you don't want to loan money to people, but you want to award grants, for instance, to researchers. Yeah.
Yeah.
And then the funding agency also needs to take decisions. And obviously, it also wants to take the optimal decision for the investment that they are going to do. Yeah.
Yeah.
And there were a few years ago, a few papers of people that recommended that in the case of research and innovation, the best strategy is not to keep giving money to let's call it the best researchers around that are well established, but to introduce an element of randomness. Yeah,
Sure.
That at some stage you start giving funding to people that probably under normal conditions would never have received a grant, because they might come up with a crazy idea that is very successful. Yeah. Banks don't operate like that.
No, banks don't operate like that, because you know, whether so what does a crazy idea mean in terms of loan? The person is going to pay back.
Yeah.
Right? So that's not a great reward function, right? Whereas for a funding agency, there's a great reward function where the person does better research than, let's say, traditionally good application, right? So it's almost like a genetic algorithm kind of scenario, right? Where you break the best just to see if you could get a better reward later.
Yeah.
Right?
Yeah.
But banks don't have that reward function.
But you know, if there were studies on the kind of random decision-making process?
So not, I mean, there were some things that banks did where they did give random kind of loans. And that's because, you know, if I'm a bank, let's say I give only loans to everyone who earns above 250,000 as an example, right? Yeah. That means I don't really know what the behavior of people who earn below 250,000. Yeah. So sometimes what they do is they give loans to the population they normally don't give loans to, so they can learn about the universe of people. Mm-hmm. So so that, you know, in future model building, they can put those kind of variables into the model, right? Because you might find new variables about them that actually says income is not the greatest predictor. There might be something else. Yeah. Right. So in terms of figuring out the universe of applicants, they've done that random offers, but not as far as I know in terms of maximizing normal profit on a normal operational basis.
Thank you. Amir, I see there is one last question.
Yes, there's one from Camille. So he asked, what if it happens that the first offer is the lowest offer? Then one has to necessarily change his or her rules of choice. This might be a reason for change of behavior.
Sure. So if you get the first offer is the best offer, you don't know that, right? So you wouldn't change your behavior at that point because you haven't seen the other n-1 offer. But if you keep on seeing the first offer as the best offer, then over time, yes, you're right. You might change behavior and go to a different decision rule, because you might go, okay, you're based on your experience, the best offer is always the first offer. Yeah, you're right.
Okay. Wonderful. Then I think there are no more questions at the moment, and I'm sure that if people come up with new questions, they know now where to find you, and they will probably send you an email. So Kanshu, thank you so much for the very interesting talk with real life applications. So we will, next time the email with an offer comes, we will count a little bit longer before we click accept. And thank you, Amira, for helping moderating the question. Thank you, Ilya, for being here as well. And I also would like to thank the people behind Zoom that made all these events possible. Yeah, thank you to you as well. Yeah, so
thank you very much. To you as well, Professor. And thank you, Amira and Professor Siniaski. And also, you know, a big thanks to Rene Kotzer, who helped me with, you know, figuring certain things out.
And Rene and Eli and Farah, yeah. Okay, no, thank you very much. All the best, and we will definitely stay in touch. Thank you. Bye.
Bye-bye.
Bye. Cheers. All the best.